Okay, this video is going to be an overview of Lab 15, Exercise 24. We are comparing AC and DC circuits and looking at various AC waveforms. Looking at a very simple series circuit here. We have a 10k ohm resistor here on the positive side in series with a 1k ohm resistor, so a total of 11k ohms of resistance on this circuit. In our DC section of the lab, we are asked to apply 6 volts DC, and that 6 volts is coming from our analog power supply right here, set at 6 volts. And the first thing we're tasked with doing is evaluating that on our oscilloscope. So we have our positive oscilloscope probe and the ground connection of our oscilloscope probe looking at the entire circuit, and we're going to look at our oscilloscope and see what we get. Now, we are currently set up at 1 volt to the division, and if there's 6 volts with a DC offset, that means the midline here is 0, where our signal's off. So I need to bring this down to 2 volts to the division, and you do see a line that appears there. That line is 3 squares over the horizontal 0. So at 3 squares or 3 divisions, 1, 2, 3, times 2 volts, we see that we have a 6 volt signal coming across the screen there. So again, 3 squares times your volts to the division, that's 2. So we have 6 volts, and that does match up. Notice that the DC signal on the oscilloscope appears as a straight line. Okay, you're asked to look at the voltage drop across both the 1k ohm and the 10k ohm. So let's first evaluate the 10k ohm on the oscilloscope. We'll come back up here to the oscilloscope. Notice our waveform, when we move that ground clip, our waveform still a straight line, and I didn't change our volts to division. We are 1, 2, and not quite 3. We're above the half mark there. Okay, and so we know that this is about 5.5 maybe, somewhere close to 5.5. We can use the oscilloscope to dial that in a little more exact. Since I have the digital voltmeter set up here, we'll do a quick assessment with the digital voltmeter to see it's 5.47. So we're pretty close by saying 5.5. Now we're going to evaluate. Let's move our probes here. We're going to bring our multimeter hook back over here, our ground hook over here, and our oscilloscope probe is going to move there. Now the oscilloscope probe is evaluating the 1k ohm, and when we look at our oscilloscope signal at the 1k ohm, we see that we're just a very tiny amount above the 0 mark there. It looks like we're one section, one little hash mark above the 0. Now, this is zoomed out too much to know exactly what that value is, so we can change our volts to the division and get a little more precise here by going 1 volt, but that still doesn't quite give me enough. You can see I'm just above halfway, the halfway mark there. So we can say, well, maybe this is 0.5 something. Let's dial it in and get a little more precise. At 0.5 for the division, yeah, we're pretty much on the 0.5 line. Okay, and if I go at 0.2 for the division, what that means is each one of these little lines here is 0.2. That would be 0.4. And so we can dial in here. You see we're at, and this is 0.6, so 0.5 would be a little midway, or maybe we're 0.54 to that end. Certainly I could dial it in more precise if I needed to with the oscilloscope. Since I have my digital multimeter over there, we're doing a little comparison. Let's move the multimeter probe and see what we get over top of that. There we are. We're at looks like 0.54. And Kirchhoff's law says that the sum of the voltage drops equals the total voltage. So that does make sense that if we were 5.447 and 0.53, we're adding up to 6 volts that way. Our oscilloscope showed us that as a straight line, and our digital multimeter also proved Kirchhoff's law. So the series portion of this circuit showed us that a DC signal on an oscilloscope is a straight line, and it also we were able to evaluate Kirchhoff's voltage law. Let's reconfigure this for our AC source. I'll be back to you in a minute. Okay, so here we are with the circuit set up for our AC analysis. You see our oscilloscope probes are looking across the entire circuit. Our source now is coming from our BNC to alligator Y split. That is plugged into our function generator. Our function generator has been set at a frequency here of 500 hertz, so we're about 0.5 times 1K gives you 0.5K, which is also 500. Our function mode is a sinusoidal waveform right here. And when we look at our oscilloscope, which has been set up now at 1 volt to the division, we've got a DC offset, so we're splitting our signal in the middle. We have adjusted using our trigger level here, we've adjusted our pickup level so that our pickup level is right at the 0 mark there. And looking across, counting your number of squares, 1, 2, 3, 4, 5 squares for a half cycle, meaning you got a 1 full cycle with 10 squares. Those 10 squares multiplied by your frequency here of 0.2 milliseconds to the division, or I should say your time division, 0.2 milliseconds per the division, times 10 divisions, gives me 2 milliseconds for 1 cycle. If I take 500 hertz, 1 divided by 500 is 0.002 seconds. 0.002 seconds is also 2 milliseconds. So full 500 hertz waveform. Now the amplitude of this waveform is requested to be set at 8 volts peak to peak. So using the amplitude knob on my function generator, I adjusted this waveform. We are at 1 volt to the division, so vertically we're 1, 2, 3, 4 squares for a half alteration, and so we're 8 squares peak to peak. So that's our full signal, 8 volts peak to peak. Let's compare the voltage drop looking at our circuit. So first voltage drop we're going to look at should be our 10K, which is going to be the principal load. And we look at our waveform signal on our 10K, it doesn't look like our wave really dropped that much at all. And so we are going to have to dial this in a little bit to check on it a little bit further. Okay, so to get a better view or sense of what's going on here, here again is our 8 volt peak to peak signal, and it is taken off of channel 1, which was my original oscilloscope probe. And you see now I have 2 probes in here. This one, relative to the common ground, is channel 1, and that is our full source voltage. I've added an additional probe, this one right here, also to the same common, and this is looking at the 1K ohm resistor, and you see it is coming into channel 2. Now right now channel 2 has had the same exact settings. It is on a 1 volt peak to peak setting, and so let's take a look by adjusting the mode on the oscilloscope. You see my signal is showing me same frequency but a much lower amplitude, and you see that it is less than 1 volt. We're looking at a little more than maybe half volt peak to peak, let's go ahead and try to dial this in a little bit and see if we get a better view. So we're going to take this and we're going to change our voltage peak to peak multiplier. See if we can get a much more exact feeling what this is. So I'm on 0.1 volts to the division. Okay, so if we look and count from the horizontal here, we're 1 division, 2 divisions, 3 divisions, almost 4 divisions, almost 0.4. I'd probably call that like 0.338. It looks like, as we're counting above and below our divisions there. Maybe not quite, as we're looking at that. So you take your divisions above or below, and you multiply that by your volts per the division, and that's going to give you your voltage drop here. Now that's the voltage drop on this one, and obviously, as we saw earlier, you're going to see the difference of that voltage over here. So if we were at a 0.37, then what we're going to see is probably 7.6 or 7.53, I guess, would be our difference over here. So in terms of our peak-to-peak voltage, we're able to verify the same exact voltage drop with Kirchhoff's law. Now, we used 8 volts peak-to-peak versus the 6 in the DC, and the reason for that is 8 volts peak-to-peak is pretty close to the RMS value. And just to prove that to you, we've got a calculator over here. If you remember your calculations, let's take our 8 volts that we have, multiply that by 70.7%, or times 0.707, and that equals 5.656. So 6 volts was a easy number. 6 and 8 volts are easy numbers to look at. You're always going to have a decimal piece in there, but it was easy for us to take 8 volts peak to peak and compare it with 6 volts DC. And what we were able to see in that comparison is that we do see the Kirchhoff's law and the voltage drop. One final thing that we're going to take a look at here, I'm going to put the dual mode up, and it shows me, I'm sorry, I'm going to go back to channel 1 there, and on channel 1, and I'm going to bring this back to 1 division. I guess I suppose I could go the dual mode 1-to-1 in our comparison there of our 2 waveforms. But one of the things that I want to show you now is on the function generator, show you that the waveform, when we change the function to a triangle wave shape, that our amplitude still stays the same with the voltage drop. And when we go to a square waveform, we might have a little bit of a voltage drop, but I don't know if you guys can see we'll dial this guy down just one so you can see it. There's our square wave for our full function, is right there. We're seeing that the amplitudes do not change based on the wave shape that is in place there. So you see your sinusoidal waveform, your triangle waveform, and your square waveform all carry the same voltage drop with the same circuits here. So your wave shape does not affect the amplitude of the wave. All right, good luck working with this lab.